To understand the resonance of buildings during earthquakes, we will look at other resonance systems. The natural frequency of a swing makes it easy to maintain the motion using little energy. A prolonged wind swung the bridge on the right at its natural frequency until it exceeded its structural integrity and tore apart. The frequency of a wave refers to the number of waves that pass through a point in 1 second. A period is the amount of time that it takes one wave cycle to pass the given point. A frequency of 1 cycle per second has a 1 second period. If the frequency doubles to 2 cycles per second, the period is only half of a second. Resonance is a tendency of a system to oscillate with greater amplitude at some frequencies than at others. The resonant frequency of any given system is the frequency at which the maximum amplitude oscillation occurs. For example, the resonant frequency of the 1 meter long pendulum is 1/2 of a hertz. If the string were 1/4 the length, it would vibrate at twice the frequency. Small amplitudes can be approximated by this equation using length and the gravity constant. Resonant systems can be used to generate vibrations of a specific frequency to create music. Strings under tension, such as with this cello, have resonant frequencies directly related to the material of the string, as well as the mass, length, and tension of the string. The mass of the slow C string resonates at 264 Hz, whereas the thinner A string of a different material resonates at 440 Hz. Now, we use a simplified analogy of boats at sea. A series of waves, particularly when they hit broadside, can initiate rolling behavior. The smaller boat is affected by short-period low-amplitude waves that slap against the ocean liner with no effect. Small boats, on the other hand, will ride up and over long-period high-amplitude waves as the larger boats begin a long, slow rock. Now, let's look at how buildings are affected by earthquake-induced seismic waves. All buildings have a natural period, or resonance, which is a number of seconds it takes for the building to naturally vibrate back and forth. The ground also has a specific resonant frequency. Hard bedrock has higher frequencies than softer sediments. If the period of ground motion matches the natural resonance of a building, it will undergo the largest oscillations possible and suffer the greatest damage. Small buildings of 1 or 2 stories resonate naturally at much less than 1 second periods. A 1 second period will affect buildings of about 10 stories. For example, a 30-story building resonates at a period of 3 seconds, and a 50-story building resonates at a period of 5 seconds. During the 1985 Mexico City earthquake, the ground beneath the city resonated with a 2-second period for over a minute. Thus, medium-height buildings with similar natural periods suffered the most damage, while short, old, weak stone buildings and skyscrapers were relatively undamaged. That proved to be what is called a resonance disaster, which is how engineers describe the destruction of a building by seismic vibrations at a system's resonant frequency. It is because of prolonged energy input that the system swings more and more strongly until a structural load limit is exceeded. A key point here is that small buildings on hard rock and large buildings on soft sediments may suffer more damage and ground motion effects from an earthquake than small buildings on soft sediments and large buildings on hard rock. Resonance is one factor that contributes to earthquake damage. Of equal or greater importance are building design and the quality of construction materials. By determining the resonant frequency of the ground beneath the building site, the building design can be modified so that a resonance disaster does not occur. The following demonstration shows how to model resonance in the classroom.
The idea of the BOSS model is that different height buildings will respond to different frequencies of horizontal ground motion. A tall building will respond to very slow or low frequency oscillations of the ground. So if I move the base slowly back and forth, I can get the tall building to oscillate, where the intermediate and short buildings are not moving. If I move it more briskly, I can dial in the rate of horizontal oscillation so that I move the center building, the intermediate height building, and the short and the tall ones are barely moving. To get the short building to oscillate, You need to move the bass very briskly back and forth and dial in to the natural frequency of the short building, and we can see that the intermediate and tall buildings are barely moving.
House built on a weak foundation will not stand, oh no.